In this next section, we're going to learn how to solve quadratic equations by graphing. And just like we've learned last chapter, quadratic equations can be written in the form ax squared plus bx plus c equals 0. And so long as a does not equal 0. If a equals 0, then there's no x squared term, and then the equation is not quadratic. So this is really going to build on the skills that we learned last chapter, where we learned how to graph quadratic functions. And so if we want to graph x squared plus 2x equals 3, the first step is going to be to make sure this is written in standard form. So I want this to be x squared plus 2x, and I need to subtract 3 from both sides of the equation. So minus 3 equals 0. Now that this is written in standard form, I want to graph this as though it were a function. So imagine that this 0 isn't 0 anymore. I'm saying y equals x squared plus 2x minus 3. And then I can look at trying to solve this. So remember that your vertex is going to be located at x equals negative b divided by 2a. My b value is 2, so it's going to be negative 2 over 2 times a, and my a value is just 1. There's no coefficient in front of the x squared term, so that's just 1. And that means my vertex is going to be at negative 2 over 2, which is negative 1. So my vertex is going to be somewhere along this vertical line here. To find out where exactly my vertex is, I need to plug in that value, negative 1, for x back into my original equation. So I'll do negative 1 squared plus 2 times negative 1, minus 3. And the y value of my vertex is going to be 1 minus 2 minus 3 is negative 4. So the vertex is at negative 1, negative 4. Here's my vertex. Remember, it's very easy to get the kind of y-intercept for these equations, because the y-intercept is when x equals 0. So if I do 0 squared, this is going to be my y-intercept. 0 squared plus 2 times 0 minus 3. So 0 squared is just 0, plus 2 times 0 is still 0, minus 3 is negative 3. So 0 comma negative 3 is going to be an intercept. So 0 comma negative 3 is a point on the graph. And of course, since parabolas are symmetric, then negative 2, negative 3 must also be a point on the graph. Of course, I need to find the x-intercepts, so I need to kind of extend this graph a little bit more. I've already tested negative 1. I've tested 0. We've tested negative 2, also gave us negative 3. So I'm kind of testing different values of x and y. So I can just kind of extend this, maybe another value out. I can test positive 1, plug that in, and that sure enough gives me my x-intercept. If I plug in the value negative 3, that gives me an x-intercept as well. So my parabola looks like this. And because my x-intercepts are at x equals negative 3 and x equals positive 1, then those are the solutions to my equation. So notice in this example, there are 2 solutions to my equation because the parabola intersects the x-axis twice. That doesn't always happen. It is possible to have just one solution or to have 0 real solutions. So let's look at a couple other examples and see if we can see what those graphs look like. X squared minus 8x equals negative 16. If I'm trying to solve this by graphing, then I'm going to do, let's see, x squared minus 8x plus 16. Add 16 to both sides of the equation so that I have this written in standard form. I can use the same strategy that I did before, finding out where the vertex is, and that's going to be at, I want to do negative b over 2a, and so negative 8 over 2 times 1 is going to be positive 8 divided by 2, which is positive 4. So if I plug the 4 value, so this is the y value of the vertex. I just plug 4 in, 4 squared minus 8 times 4 plus 16. That's actually going to give me 0. So my vertex is going to be at 4, 0. So there's my vertex. And I'm just going to test some x and y values on either side of that vertex. I'll test positive 5, positive 6, and positive 3 and positive 2. So getting a couple extra values here. Those are both 1. These are both 4. So my parabola is going to look like this. And you can see here with my poorly drawn parabola that there's only one x-intercept this time. The only x value where the parabola touches the x-axis is when x equals 4. In this next example, I've got negative x squared equals 2x plus 4. Rearranging this so that it's in standard form, I'm going to add x to both sides of the equation. I'm sorry, x squared to both sides of the equation. So I'm going to have 0 equals x squared plus 2x plus 4. And graphing this, I'm going to, once again, just vertex is going to be negative b divided by 2a. So negative 2 divided by 2 times 1, that's going to just equal negative 1. So my axis of symmetry is going to be there at x equals negative 1, and I need to figure out the y value by plugging negative 1 in for my values of x. So it's going to be negative 1 squared plus 2 times negative 1 plus 4. And my y value is going to be 3. So my vertex is going to be at negative 1, 3. Negative 1, 3. Let's find some other x and y values to test here. It would be fairly easy to get the x-intercept again by plugging in, I'm sorry, the y-intercept by plugging in 0 where I have x. So I'm going to find out that this is a point on the graph. Let's say negative 1 gives me 3, 0 gives me 4. So negative 2 must also give me 4 as an output value. And kind of running out of space here on my particular axis. But it doesn't matter. I can already see that this graph, this parabola is concave upward. It's never going to intersect the x-axis. So there are no real solutions to this particular equation. There are no places where this parabola intersects the x-axis. So we can see here from these three graphs of the parabola graphs, this first one intersects the x-axis twice, so there are 2 real solutions. This parabola intersects the x-axis once, so there's 1 real solution. And this parabola never intersects the x-axis, so there are no real solutions. By the way, in chapter, from one of the chapters from last semester, we did learn about treating each side of the equation as though it's a separate graph, and then seeing where those two graphs intersect to solve the equation that way. And so it is possible to kind of look at each component of this equation and graph it separately and seeing where those graphs intersect. That's another strategy um, uh, for solving equations in this way. So if I drew the parabola that for negative x squared, negative x squared would have a vertex here, but it opens downward because it's got an a value of -1. So graphing negative x squared would look like this. And then if I wanted to graph this is a straight line. It's 2x plus 4. Remember what we learned first semester? That means my straight line has a y-intercept of 4, and the slope is 2, so I go up 2 over 1, or sorry, up to right 1 or down to left 1. So my slope kind of looks like this. Try to draw a straight line here through those points. Not perfect, but you get the idea. Those two graphs never intersect. So I can see by graphing each of these as a separate line that there are no points of intersection. So there are no real solutions. Okay. And this strategy would work for the other examples as well. Rather than kind of adding or subtracting from both sides of the equation to get the parabola written in standard form, we could instead just graph each side of the equation separately, see where they intersect, and evaluate the graphs that way. So these are different ways to solve quadratic equations by graphing. Now, all the examples we've looked at so far have nice whole numbers as solutions to the equation. Many quadratics do not have nice whole numbers as their solutions. We're going to find out how to calculate those more precisely in a later chapter, but for right now, we're going to show some methods for kind of estimating those values. So here, if you think you can read the numbers, fine, off of the graph. Like here, this seems to be a value of x equals -1. Here, the intercept seems to be +2, and here the intercept seems to be +3. You can always check to see if your answers are correct by plugging them back into the original equation. If these are truly x-intercepts and you plug those x values back into the original equation, you should get 0 as your y value, 0 as your output. So let's try it. If our function is f of x equals x minus 3 times x squared minus x minus 2, then I can try plugging in the value -1 because I think that's what this point looks like on the graph. I can plug that value in, and then I can plug in -1 everywhere I see x, and just leave the rest of the equation the same. I've got a squared here and -2 here. So -1 minus 3 is just -4. -1 squared is +1, minus a -1 is +1 minus 2. And I can see that f of -1 does actually cause this term to become 0. So that does actually equal 0. So x equals -1 is in fact one of the solutions for this graph. Let's test the next one. Next, we're going to test f of 2. So if I plug in 2 everywhere I see x, 2 minus 3 is going to be -1. 2 squared is 4. Let's say -2 minus 2. I can see that this term here, 4 minus 2 is going to equal 0. So 0, it doesn't matter what this subtracts up to being 0 is going to times that -1 is going to give us 0. So 2 is in fact a solution to this system or to this equation. And lastly, let's try checking that last 0, which is 3. What's f of 3? I'm going to have 3 minus 3 in parentheses. Let's see, 3 squared is 9 minus 3 minus 2. So this time, this first term is going to equal, or this first um, subtraction problem in parentheses is going to equal 0. So it doesn't matter that this other number equals 4. 0 times 4 is still going to give me 0. And in fact, 3 is also a solution to this system of equations. So we know that -1, 2, and 3 is what the solutions looked like on the graph, but I was able to check them and confirm that they are truly solutions to this equation. This next example, I see here that I've got a value between kind of -3 and -4, but I don't know exactly where. And I've got a value here between 0 and -1, but I don't know exactly where. And so what I can do, when I see that there are negative values being produced when I plug in these values of x, like -3, but positive values for y when I plug in more negative values of x, like -4, -5, -6. I know that there must be a 0 in between -3 and -4, but I don't know where exactly. And so what I need to do is test a bunch of different values of x. Plug a bunch of different values of x into the original equation. F of x equals x squared plus 4x plus 1. Just test a bunch of them out and then go with the value that's closest to 0. So this problem kind of gave me permission to round to the nearest tenth if I needed to. So I'm going to test a bunch of values between 3.0 and 4.0. I'll test -3.1, 3.2, 3.3. These are all negative values that I'm testing here. And I've got some of those solutions pre-written for you, but many of you need to practice doing these problems on your calculator. So try plugging in -3.5 where the x is. So -3.5 squared plus 4 times -3.5 plus 1. And if you do that on your calculator, you should get about -0.75. So we'll plug that in here, -0.75. Test those other values out. Try -3.6. You should get -0.44. Try -3.7. You should get -0.11. Try -3.8. You should get positive 0.24. So we know that the change happens, the 0, the solution occurs between -3.7 and -3.8. I'm allowed to round to the nearest tenth, so I'm going to choose whichever value is actually closer to 0. Here, this -0.11 is closer to 0 than positive 0.24, so I'm going to go with -3.7 as one of my x values. And I'm going to do the same thing for the other x-intercept. I'm going to test some values between 0 and -1. And I've partially filled in this table for you, but we'll plug in some more values. If we plug in -0.5, that gives us -0.75. If we plug in -0.4, we're going to get -0.44. If we plug in -0.3 for x, we'll get -0.11. And if we plug in -0.2 for x, we'll get positive 0.24. Once again, we can see the changeover is happening here, but the -0.3 value gives us an output that's closer to 0 than the -0.2 value. So the x value we want to write down for our answer is -0.3. And those are the solutions that those are the solutions to this equation, at least approximated, rounded to the nearest tenth. Notice because our vertex here was at exactly x equals -2, um, these numbers value-wise turned out to be the same as these numbers. That doesn't always happen. It's because this vertex was a nice, at an x value that was a nice whole number. And so it was symmetric on either side of that whole number. But if your vertex isn't at a whole number, then you won't spot that same symmetry. So don't assume that your values for both zeros are going to mirror each other in the way that this problem did. All right, let's look at a real life example. An athlete kicks a football 2 feet above the ground. So this is like punting where they kind of drop kick the football um, with an initial vertical velocity of 75 feet per second. And we've got a function here to represent the height in feet of the football after t seconds. So we're supposed to find the height of the football each second after it has been kicked. So we've got the initial height is going to be 2 feet because that's where the ball started. But then I can talk about 1 second after kicking, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Let's start with that. And then if we need to extend the table, we can. We basically want to plug in these different values of t into our original equation using our calculator and finding what the height is. So if we plug 1 in for t, we're going to get 61 as our output. When we plug 2 in, we get 88 as our output. When we plug 3 in, we get 83 as our output. Plug the number 4 in, we get 46 as our output. And plug 5 in, we get -23 as our output. Of course, this doesn't make sense in the context of this real world problem. No sense for this one. So this must mean we've already kind of crossed the x-axis. It's already hit the ground and the football's already stopped moving. So we've done this by filling in the table over here. Then the problem says, estimate when the height of the football is 50 feet. Okay, well, from looking at this data table, I can see that to get from 2 feet high to 61 feet high, I had to hit the 50 feet mark somewhere between t equals 0 and t equals 1. So between t equals 0 and between 0 to 1 seconds, that's one time where we hit 50 feet. But of course, whatever goes up must come down, and we're going to hit 50 feet again between 3 and 4 seconds. So we're going to hit 50 feet 2 times, once between 0 and 1 seconds, and another time between 3 and 4 seconds. All right, so I want to know more specifically than this. So I'm going to kind of use a graph to kind of figure out when the height is going to be 50 seconds. I'm going to do this by saying I want the height to be 50 seconds for this equation, -16t squared plus 75t plus 2. Of course, if I want to graph this as one parabola, I need to write it in standard form. So I'm going to need to subtract 50 from both sides of the equation. And I'm going to have 0 equals -16t squared plus 75t minus 48. Okay. So let's graph this now using some, I'm going to graph this using technology, and then I'll kind of transfer it over here so that you can see what it looks like to make sure you've plugged it into your graphing calculator correctly. So this appears to have a peak at kind of just over 2 seconds. And the peak appears to be around just under 40 feet high. And we seem to have a x-intercept at just under 1 second, and then just under 4 seconds, like this. So our parabola approximately looks like this. And then using the trace feature on the graph, you can trace the values along this side and along this side to get a more precise reading of what those x-intercepts are. And the x-intercepts appear to happen at about x equals 0.75 and at approximately x equals 3.9 seconds. So after how many seconds is the football 50 feet above the ground? Our solution is 0.75 and 3.9 seconds. I hope this helped.